never one to fall to pieces. I'm always steady as she goes. I listen hard to all the teachers. The more I learn, the less I know.
Well, with that introduction, welcome to another Math Teacher to Go. We are in the third part of our series on the chain rule. Today, we will look at chain rule part 3, trig functions. We're going to talk about what happens when you put a function inside of a trig function and how do you deal with the chain rule with that. Some students find this very confusing, though it's really not that bad. So, let's remember the rules for taking the derivative of the 6 trig functions, and I apologize for the lack of spacing here, and it could have looked a little nicer, but if I take the derivative of the sine of x, I get cosine. The derivative of cosine is negative sine. The derivative of tangent is secant squared. The derivative of cosecant is negative cosecant times cotangent. The derivative of secant is secant times tangent. And the derivative of cotangent is negative cosecant squared. You should commit these to memory. Now would be a good time to do flashcards or Quizlet or something like that. Okay, so now let's see how the chain rule applies to these. Notice all of these are take the derivative with respect to x, and the derivative is just simply the function with the x in it, and all of the functions, sine is just sine of x, cosine is just cosine of x. So there's no inner function. The derivative of, if you call the argument the inner function, its derivative is a 1, so the chain rule is kind of unnecessary. The chain rule becomes important to trig functions when the argument, when we say sine of x, we mean the x is the argument, what you're taking the sine of, for instance. When that argument is a function of x. For example, sine of x cubed plus 2x. The derivative of sine is cosine. Now the inner function is x cubed plus 2x. If I gave you something for x, you would cube it, you would multiply it by 2, add those two things together, then take the sine. The last thing you would do would be to take the sine. So the first thing you do when you take the derivative is say, what's the derivative of sine? It's cosine. So you write cosine, and you keep the inner function the same. It's the cosine of the same thing you had the sine of, x cubed plus 2x. Then you're going to multiply by the derivative of the stuff inside. Cosine of x cubed plus 2x tells you how sine of x cubed plus 2x changes when x cubed plus 2x changes by 1. But you really want to know, how does y change when x by itself changes by 1? So you have to take that first part of the derivative and multiply it by the derivative of the inner function, which is x cubed plus 2x, or the argument of the trig function. That's where this 3x squared plus 2 at the end comes from. That's our chain rule kicker. I've been saying that once in a while. So traditionally you write the 3x squared plus 2 out in front of the trig function. It's just easier to see it's not part of the trig function. And make sure you put parentheses around this, because the cosine gets multiplied by all of 3x squared plus 2. It doesn't just get multiplied by 3x squared and then you add 2. You have to be aware of order of operations when you do this. Okay, so sine is the outer function. When you take the derivative, the cosine, you get the cosine of the same function. Then you multiply by the derivative of the inner function. Example 2. If y is the cosine of e to the 3x, so we get a couple things going on. We get a cosine, we get an exponential, and that exponential has a power that's not just x. Well, the derivative of cosine is negative sine. You keep the e to the 3x the same. Then you look at the e to the 3x and you say, well, what's the derivative of e to the 3x? Well, it's going to be e to the 3x times the derivative of the exponent, which is 3. So that one actually had two inner functions. The 3x was the inner function of the exponential, and the exponential was the inner function of the cosine. You work your way in from the outside. Cosine is on the outside, so you take its derivative first. E to the 3x is next, so you do e to the 3x next, and then the 3x is next, so you multiply by the 3. I didn't write out all the steps there, but after you see a couple of these, you'll begin to get the idea. Y equals secant squared, y equals secant of x squared plus x is my next example. So the derivative with respect to x is secant, the derivative of secant is secant tangent. Notice it's secant of what was originally the argument times tangent of what was the original argument, and then multiply by 2x plus 1. In general, if u is a function of x, you get these for the derivatives. Okay, now I want you to stop the video for a moment and try cotangent of 3x minus 7 and tangent of e to the x. Try those and then come back and we'll see if you're right. I've left the rules up here in case you don't remember them. So stop. Okay, are you back? You're back. You sure you did these? Because here come the answers. The first one is cotangent of 3x. The derivative of cotangent is negative cosecant squared. So I get 3x minus 7. That was cotangent 3x minus 7. I keep the argument the same. And the derivative of the 3x minus 7 was 3. For tangent e to the x, derivative of tangent is secant squared. I keep the argument the same. So it's secant squared of e to the x. Then I have to remember to multiply by the derivative of what's inside. That could be tricky because you're looking at it and kind of thinking you already did that because e to the x is its own derivative. But it's secant squared of e to the x times the derivative of e to the x, which is just another e to the x here. Okay, I hope you've learned something from this edition of Math Teacher to Go, and I'm sure I'll be seeing you again.